Welcome to Physics AP1's first video for the second unit, and we are dealing with forces, static forces this time. And it's the first video of the unit, and we need a toy. This is our toy. We will play with it in class. But right now, all we need to know is that when we hang it by a string, it just sits there. That's a toy. On to the physics. Last unit we talked about motion, things moving, because that's what our toy was doing, but we neglected to talk about where it came from. How are things moving? So I have to go back now and talk about forces, the things that cause motion. Except in the first one, they're not going to cause motion. We're going to have two forces that cancel each other out. Don't cause it to move. Our toy, our pig, doesn't move if he's behaving himself. When we hang him, he'll move later. Look, he's got wings. It's going to be fun. But for right now, he's not going to move. That's statics. That's what we're doing this time. And when we're dealing with statics, we have to deal with sigma F. Sigma F right here means sum of the forces. Sigma means sum of. So we're going to add a bunch of forces together, and if they equal 0, it's statics. So let's start off by defining a force. A force is something that could cause motion. In this first one, we're going to set them equal to 0. But it could cause motion if it wasn't canceled out. It can be a lift, a push, or a pull. And force is a vector. We know what that means. That means it has to have magnitude, unit, and direction. So all that component stuff that we talked about last chapter, we're going to do with forces as well. It's our fourth vector. And notice that if we were doing our set units before, we would have kilogram meters per second squared, and we'd have to write that every time we did a force. People got tired of doing that because you do a lot with forces, and so they invented a unit, Newton, that is defined as kilogram meters per second squared. And it brings up a good point. It brings up a goal for you as a scientist. Newton's was named after Isaac Newton, who invented most of the science that goes with forces. If you became famous later in your life, you might have a unit named after you. Or, if you would prefer, you could name your unit after your favorite physics teacher. I hereby give you permission right now. You have permission. You can do it. Here is a list of all the forces we're going to deal with this year. And a general description for force, and then the symbols we use for them underneath that. And I like to use all the ones with F's. I like forces to be F's with little subscripts, and everyone has a different one that sort of describes what force it is. But AP uses other letters for them, like N for normal force, or W for work, all sorts of different things like this one and that one. So you have to know that sometimes they're going to do that. A lot of those are familiar, gravity, and friction you've probably heard of. Some of them not so much. These two down here we're going to save for second semester, but all of these are going to be the ones we're going to deal with, and we're going to go through them, and we're going to do them in the order that we are going to write them onto free body diagrams, which is what we're going to use to study forces. So we're going to go through all those. You can also just have a force that you define as like F sub H and call that force of the hand, and that's just kind of a kind of force that you just have to give a number for. So let's say the force of the hand is 5 newtons down, or whatever it is you're going to do. So these plus anything you're going to add that you could just have an external force, sometimes you call, right? Oh, and here's Newton. That's a picture of the man himself. Here he is. He has a unit named after him. Why don't I? So sometimes when you have a complicated object like a flying pig over here, you need to simplify things to be able to talk about them. So we do a free body diagram. A free body diagram, first we simplify our object. We take a big pig with wings and we make him just a little red ball. Free body diagram. I'll make a simple drawing. And if you have an object that's at an angle, you need to draw it that way in your free body diagram, just because that's how you can tell where the forces are going to move it. In this case, we just have a circle, so we're going to leave it that way. Determine all the forces that are acting upon your object. In this case, we know gravity because we're on Earth. There has to be something that's pulling it back up. That's the force of the rope, which we call tension. We put on our free body diagram and we label it. And notice that we put them the direction that it's going to pull. All of our arrows go away from our object, so we know which way they're going to force our object. And notice the relative size matters. And so I made my tension and my gravity the same length, so I know that they're canceling each other. So that's important. That's the relative size. And so if we had a really big force, we'd make a long arrow. In this case, they cancel. Don't put other vectors on there. If you have a velocity or an acceleration, don't put on your free body diagram because that's going to confuse you. Only forces go on a free body diagram because you want to find out how the forces balance each other. And you need to mark the positive x and y. I put a plus up here because we're called up positive and down negative. If you have forces going right and left, you'd probably want to label right as positive. You could do this arrow and put a plus there too for x and y positives. And you need to do that so you know, because the free body diagram is how we get our signs for all of our force diagrams later. Now we're going to go through all of the forces that were on our force diagram, the chart earlier, and we're going to do them in the order that we would like to put them on problems, just like we had an order for our kinematic variables. We always want to do gravity first, and that's because any object on the planet is going to have that force, and so it's a good one to start with because you know it's always there. So F little g is our first one. And notice it's a really easy equation. It's just the mass, which we've already talked about the mass is in kilograms, times a constant g, which we've already talked about also. Notice though that that negative that we put on in kinematics was because we defined up as positive and down as negative. So we used it as an acceleration, then we knew it had to be a negative. But the actual number itself is just 9.8. And so we put 9.8 in there and just multiply by the mass, and that's it. And notice, because it's a vector, we have to have a direction. It always goes towards the center of the Earth. Yeah. And because gravity can be between any two things, not just with the Earth, we have a generalized formula for it also. If we have any two objects, say my rhino and my stapleless stapler, they both have mass. And so if I was to let them go, there would be a force between these two. Would they go sucking together? They would not, because gravity with the Earth is so much bigger, because mass theory is so much better. But if you put them out in space, these two objects would actually come together. There are some objects that are massive enough on the Earth to move towards each other because of this force. Those giant supertankers, if you put them too close together, they suck together and hit each other, so you have to put those little bumpers in between them. My direction on my little force between these two things is together. Notice the distance is between their centers, not between their outsides. That's why, you know, the distance of the Earth is all the way to the middle. And the reason why this force is so small is because of this number here. 6.67 times 10 to the negative 11th. That means a decimal 10 zeros before I can even write the 6. That's really small. So there's not much force between those. To see the force, usually we have to have the mass in the same order as 10 to the negative 11, or positive 11 instead of negative 11, like the Earth or other massive objects. One more quick thing on this. It turns out these formulas are actually the same. If I took my F big G formula and put in G times the mass of the Earth times any other mass divided by the radius of the Earth, which is essentially the distance between the centers squared. Notice all of this together equals little g. So essentially we're taking a pretty complicated equation, the big G equation, making it simpler because we want to use it a whole lot of times. And these things, the mass of the Earth and the radius of the Earth, aren't changing, so we get a nice easy number, 9.8. Nice. The next force we're going to deal with is normal force. Normal force only exists if there's some kind of surface. If we have a surface and we put an object on it, stapleless stapler, we know that gravity is going down, but it's not moving, so something must be pushing back up. That something that's pushing back up is called normal force. And so normal is a math term that means at 90 degrees too, so normal force is always 90 degrees to whatever surface it is touching. We can sometimes think of normal force as the surface force. Gravity needs to be somewhere with mass, like we're on the Earth. Normal has to have a surface so we don't deal with it at all. But if there is a surface and it's touching the surface, there's going to be a normal force. And it's what's called a matching force. So if I have my stapleless stapler just sitting there, I know there's a normal force that exactly cancels out gravity for it. But if I put something else on top of it, like my rhino, I know the normal force has now gotten bigger because neither one of them is moving. And when I do mg for this, the mass is greater, so the mg is greater. Normal force matches it. The more things you put on top, the more forces you have there until the surface breaks, right? And if I take another thing like, I don't know, my hand, here comes my hand, wah, 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 wah. Beautiful hand, and I have that force going down also, F sub hand, my normal force then is going to be the force of hand plus the force of gravity. So normal force doesn't have an equation. You always get the equation from your free body diagram. So that's one of the reasons why the free body diagram is so important. If we have an object with gravity going down, and we take our hand, and instead pull upwards, force of hand, then the force normal doesn't have to be as big to cancel out gravity. And so we end up saying that the force of the hand plus force normal is going to equal force of gravity. And so you always set up an equality. Normal force is going to make the two sides equal each other, whatever forces are where. And so it kind of is like it matches things up. It makes sure things cancel in both directions. And so it varies itself so that everything equals. So one little wrinkle in normal force is, what if my surface is at an angle like this one over here? If I take my surface and put it at an angle, normal force still has to be at 90 degrees because that's what it's defined as. So my normal force still goes this way, which means that normal force can't cancel out gravity because it's going in two different directions, right? So gravity goes straight down. Normal force goes 90 degrees. That's not going to be able to cancel it. So what ends up happening is this. Normal force cancels out the part of gravity going this way. And so we have to do components again. And what it doesn't do is it does not cancel out the part of gravity going this way. So that part is still there. So the reason why my little thing slid down the incline is, doing your most nerdy voice, the reason why an object slides down an incline is because the normal force cancels out the portion of gravity that's going into the incline, leaving the other portion of gravity available to slide the object down the incline. So we already had another force that was a matching force, that is tension. Tension is a matching force that is only applied on ropes. So before we said we had gravity going down and we knew that the pig wasn't moving, so there had to be a force going up. There was a rope there. So like a normal force is a surface force, tension is a rope force. And it matches. So if I put two pigs on there, my tension would increase to cancel them out. All matching forces make sure that whatever's going up and down in whatever direction they go gets canceled. And if you have a rope, like if you had two ropes, one going that way, one going that way, the tensions would be constrained along those ropes. Call it tension 1, force, tension 2. And they would make sure to cancel out anything going the opposite direction to them, just like normal force cancels out anything that's going opposite the 90 degrees to the surface. So our next force is friction. We couldn't talk about friction until we knew normal force because our formula for friction, and this is another one that actually has a number we can get from a formula, is mu times F of n. F of n is how much you push two objects together, and mu is a constant based on what two substances are rubbing. If you have metal on ice, there's not a lot of mu, it's a small number. If you have two pieces of sandpaper, mu is large. I'm saying mu as if you know what it is. Here, let's draw it a little bigger so you can see what mu is. I'm going to say it a lot, so you need to remember what mu is. One way to remember it is kind of stupid, but here we go. If we give it two eyes, a nose and whiskers, and a little mouth, it looks like a cat because it's got two ears, and cats say mew, mew. So the direction of frictional force is always opposite the direction of motion. So if you take your hands and you try to push them, your right hand downwards, friction's going to go back left. And it always goes opposite motion. So we need to know which way the thing is moving or try to be moved before we can know which way friction goes. And there's two types, static and dynamic. Static is an object is not moving, and dynamic is after it moves. And they're treated differently. Static is a matching force. So if we have an object, we take our hand, and we try to push it that way. It takes a little bit of pushing before it starts to move because there is a force backwards. That is the force of friction static. and it's matching up to this amount. So it can be less than that amount. So you can't ever use this formula for static friction. For static friction, you need to do the same thing you do with normal force and with ropes, is find every other force. In this case, it says my hand is pushing at 2 newtons. The frictional force has to be 2, even if mu f of n is 5. 5 is its maximum value. Now, once it starts moving, once we have some motion in an object, let's say we're going, ooh, that is not very good. Let's say we're going down a hill. Once it's moving, dynamic is a constant value. So once our friction is for a moving object, it is mu f of n always. So not moving, it's static, it's a matching force. We don't use the actual formula, that's just the maximum it can be. Sometimes they ask you when it starts to move, that's when it's at its maximum. Constant is when it's moving, it has the value mu f of n. You can find an actual number and use it in your problems. Those are 2 different types. So I have a lot of examples of this, so I think you'll get it a little better later. One last force is spring force. Spring force is another one that opposes motion. If you have a spring attached to a wall and an object and you pull your object this way, there's going to be a force back the way that it came, which is the force of the spring. And all it is a constant based on the spring, how many coils it have, what it's made out of, that's the K, and then multiply that by how much you stretch it, X. Not how long the spring is, but how much you move it from its unstretched length. You multiply those two together, you get the force of the spring. It opposes motion, probably the easiest force we have, except that it's not constant. It changes as you pull it farther out, so that's why we can't use kinematics on that spring. We'll get to energies next unit, and that's what you use mostly for springs. But you can find the magnitude of a force of a spring by taking the constant times how long you stretch it.
Snack time!
As you know, I am a nut, or I like nuts. Almonds we've already had. Cashews I may like even more than almonds. They don't have them much because they're kind of expensive. I was curious about why cashews are expensive, so I did a little internet research. This is a cashew fruit. Can you believe that? Every cashew that you eat, every little thing like this that hangs down from like that, yep, is this little green thing right here. Can you believe that? It's kind of crazy. It's like on the end of a squash or something. That's one of the reasons they're expensive, because you gotta take one for every big giant squash that you have. But the real reason that they're expensive is they grow on vines that are related to poison ivy. See that poison ivy? Don't ever touch that if you see that. And it turns out that the people that harvest cashews have to wear all sorts of gloves and protective safety gear so they don't get essentially poison ivy. It's urushiol oil that comes from the vine that cashews are on. Even when they wear all this stuff, they always are getting stuff on them. It burns, it itches, it's awful. If you've ever had poison ivy, you know what I'm talking about. That's why cashews cost so much. People are putting their lives in danger for you and your nuts. Don't take them for granted. Since forces are vectors, we need to go over how to add vectors. And because forces go in other directions that we haven't really talked about with our other vectors, I'm going to go into a little more detail. When we add vectors, we can put them first one and then the other one and add them graphically. So if we want to add this one with this one, we'd first draw that first one, which went like that. Then at the end of that one, we make another coordinate axis and we put this one. And the resultant is basically the dotted line that goes from the beginning of the first one to the end of the last one. We call that putting them tip to tail. So you put the beginning, the second one at the end of the first one, and the dotted line shows you what the resultant would be. If you really carefully drew them, you get really great answers for that, but it's really hard to do in general. There's one case in which we can do math to make the exact answer right, and that is when our two vectors are in the x and y directions, we can make it work. We can take these two vectors that are in the x and y direction and put first the y one, this one here, going up, and then the x one at the end of the y one, and then we make a nice right triangle, which is basically what we did last chapter when we wanted to do an easy one, last unit. And then we could do a squared plus b squared equals c squared. We can do inverse tangent to find the angle of our resultant, which is this dotted line that's right there. Now, if they give us a whole bunch of ones that are this way and that way, we can add all the x's together first. We can add all the up and down ones to the y, and then we can do one a squared plus b squared equals c squared. That's what this is telling us right there. We'll do an example of that in class, but it's pretty easy. That's no problem. Things get harder if I have two vectors that are not in the cardinal directions. I can't really add those together and get an actual exact answer the way they are. But because last chapter I split a lot of v1s into x and y components, I know that each of these can be split into components. Let's say instead of 100, we're going to call this x1 and y1, and this x2 and y2. I can get rid of the two vectors that I can't really add and get four vectors that I know how to add. Because I know I can add these two x's together pretty easily because they're in the same direction. These two y's together, they're in the same direction. And then once I get my two totals, I can put them back together the way I know how to do with vectors. Let's go ahead and do that. So I went ahead and did the components for x1 and y1 with sines and cosines, and you can see how I did it there. The same way we did with v1s. This is a displacement, but I can still use sine and cosine, take the hypotenuse times either the sine or cosine depending if it's the adjacent side or the opposite side. I went after and did it for x. These are the answers for y. Make sure you know how to do that. Do it yourself really quick. Pause the video, whatever you need to do. Get those components. Once we have all those components, we can add the two x's to get an x total down here, add the two y's to get a y total, and our resultant of all four things added together is a dotted line right there, a squared plus b squared equals c squared. 93 squared plus 112 squared equals c squared. I get 146 for the length of this side, but since it's a vector, I know I have to have an angle too. And I say that the tangent -1 of opposite 112 over adjacent, which is 93, gives me 50. And so my addition of these two vectors is 146 meters, 50 degrees above the horizontal. Video's getting a little long, so I'm going to save the examples for class. I'm going to leave you with a little chair dancing. Some kind of madness. Static kind of madness. We'll talk about it in class.